Recall the definition of a limit of a function with one independent variable. Assume that f of x exists for all x in some open interval containing a, except possibly at a itself. The limit of f of x as x approaches a is L if for any epsilon greater than 0, we can find some number delta greater than 0, so that if x is chosen within delta units of a, then the f of x in the limit L, so the y value will be less than L by smaller than that epsilon value. So in other words, given a specific epsilon, so here's our limit L, this is L plus epsilon and L minus epsilon, we can choose a specific distance from A, so we'll call it delta. So this is A minus delta, this is A plus delta. So that if any x is in between A minus delta and A plus delta, and you say that by using absolute values in this way, that's just saying all the x's within delta units of the x value A, then we'll be guaranteed that the y values for this function are between L minus epsilon and L plus epsilon. So this is just the y values, and the distance they are from L must be within epsilon units. Okay, so now when we were choosing our delta, we were looking at values along the x-axis. So we had A, and we wanted to make sure we stayed within some delta of the A. So this interval can be described as the absolute value of all x minus A less than delta if we want delta to be this distance from A. And now positive just means that it's not A itself, it's around A. And of course, the absolute values will always be positive. So now, how does this translate over to functions with more than one independent variable? We still have the idea of wanting to get close to some value. So here's the point that we're trying to get the limit at. P naught, which can be given as A comma B. So that's the coordinates of the point P naught. As points are getting closer and closer to P naught, so let's just take an arbitrary point P, which is denoted as X comma Y. If P is getting closer and closer to P naught, then that means that the Z value associated with all those points P must be getting closer and closer to whatever the limit is. So now if L is the limit, as P gets closer and closer to P naught, those Z values must be getting closer and closer to L. So now how do you define getting closer and closer? We want the distance between P naught and P. Now, since P and P naught are points in the plane, the distance could be, measured by, I'll just denote it with absolute values around it. This is the distance between P and P naught. So now, that distance to be less than delta means I'm within delta of that point P naught. Well, now the distance between these 2 points we can find using the distance formula. If P is represented as X comma Y and P naught is A comma B, then this distance is the square root of X minus A squared plus Y minus B squared. And we want that distance to be less than delta. Now look at what this has given us. If we squared both sides, we have x minus a squared plus y minus b squared less than delta squared. This is just saying that we want all the points x, y within delta of the point AB. That's equivalent to saying all the points within a circle of radius delta from AB. So AB is the center of the circle, and the radius is just our delta. So we're looking at a disk here instead of an interval on the x-axis like we did with one independent variable. So now to find a limit, we are looking at points inside of a delta disk or inside of a disk with radius delta. So the function f has a limit L. Now notice the values of the function are still just real numbers. So the limit itself is just a real number, and it's just a number on the z-axis. So the function f has a limit L as p approaches p naught. So we're looking at this p in the domain approaching p naught. If the limit, now we can say the limit as p approaches p naught of the function f of xy equal to L, or we can say xy, which is the point P, approaches the point AB. And we still put the function here, and if that function had a value, you'd just put the equation for that function. It'd be an expression with x's and y's. So if given any epsilon greater than 0, so that's the distance we can be away from that limit L, we have to be able to choose a delta. So we have to be able to tell them how far from AB they need to choose their x so that the y value, the z value for the function, for the point, is within epsilon of the limit L. So we're looking at z values here. The difference in the z value in this limit L must be less than epsilon. This is assuming L is that limit. So as the point P gets closer and closer to P naught, if L is the limit, the z values are getting closer and closer to L, and we can choose a delta so that it's always within epsilon of that limit L. So now, and this is just saying that we're choosing, we found a delta, how big a radius for that circle, so that the point will be within delta of that point AB to ensure that we're within epsilon of that limit L. So our domain now is using circles, open circles, to denote distance between the point that the limit's approaching. Okay, so now let's look at just some very basic limits, and then we'll look at the limit laws. A, B, C are real numbers. If we're looking at a constant function, this is equivalent to the function z equal to c, which is just a plane that's parallel to the xy plane. If we're taking the limit of that function, so this is our f of xy, this is just saying as we get closer and closer to that point AB, down in the xy plane, what's the function f of xy getting closer and closer to? Well, this is telling us that every function's value is c. So if we want the limit of f of xy, and f of xy is a constant, then it should just be that value c. So the z values for all points in a little disk around the point AB will be c, since every z value is that function value c. Now, if you want to actually just use the definition of a limit to prove this, we can say that given an epsilon greater than 0, we can pick, so given epsilon greater than 0, choose any delta greater than 0. It's not going to matter because it's the constant function. And if we look at f of xy minus the L, now f of xy, though, is just the function c, and our limit we're contending is c, and that's 0, but epsilon was any positive number, so that's always less than epsilon. So it didn't matter what delta we chose, this value, absolute value of f of xy minus L, will be less than epsilon. So that proves that c is the limit of that function. Now, just looking at it algebraically, we've got a function here that may or may not have x's and y's in it, and we're told that the point xy is approaching AB. That means that the x value is approaching A, the y value is approaching B in this function, but there are no x's and y's. So it doesn't matter what the x's and y values are approaching, that's staying the constant c. So that limit, That's just like taking the limit as x was approaching 1 of 5. It didn't matter what x was approaching. This function has a value of 5 all the time. So all this is saying is the limit of a constant function is that constant. Now the limit of a function z equal to x. Remember, this is our z equal to x. So this is the function that we're using, and we're saying that x and y are approaching AB. Well, algebraically, it's clear to see that x is approaching A and y is approaching B if we're approaching the point AB. So if x is approaching A and the function is just x, then that means x is getting closer and closer to A. So that's pretty intuitive, and likewise, if the y is getting closer and closer to B, then the limit of the function y, which is our f of xy in this case, would just be getting closer and closer to B. Now, if I actually wanted to look at the definition, I'd say, well, let epsilon be greater than 0, and I would choose my delta to be the epsilon. And now we're choosing the delta so that the square root, this is from the definition, x minus a squared plus y minus b squared has to be less than delta. But since delta is epsilon, this is just epsilon. And now notice that this sum, x minus a squared plus y minus b squared, will always be bigger than or equal to the square root of x minus a squared, because this is always greater than or equal to 0, so that will be a larger term on the right than this is, but this, by definition, is just the absolute value of x minus a, and so we have the absolute value of x minus a is less than epsilon, but x for this function is just f of xy. And a is what we're contending the limit L to be. And so we've just shown that as long as you choose delta to be delta to be equal to whatever epsilon's chosen, we do have that f of xy minus L will be less than epsilon. So that does prove that the limit would be a in this case. So these are just the two most simple limits. We're taking the limit of a linear function and limit of a constant function. So in other words, just plug in these values for x and y in this expression and you'll get those basic limits. Now let's look at our limit laws. These will look familiar. They're very similar to the ones that we had back in Calculus 1 when we had one independent variable. L and M are real numbers, and we're assuming that the limit of f of xy is L and the limit of g of xy is M, as the point xy is approaching the point AB. So again, we're down in a disk in the xy plane, and some point AB is there in the middle. So xy is getting closer and closer. Now, it can come from any direction. We don't just have a left and right side to find limits anymore. We're approaching a point, and it could be from any direction. So now, assuming that c is a constant and m and n are integers, the sum rule applies. That means the limit of f of xy plus g of xy could be written as the limit of the f plus the limit of the g as xy approaches AB on both of those two limits. Now this limit here is just L, and the other limit is just M. So that's just saying that the limit of a sum of two functions could be evaluated by taking the limit of each function separately. Same thing with the difference. The limit of two things subtracted is the same thing as the limit of the f of x minus the limit of the g of x, because this is your limit of f of x, xy, and this is my limit of the g of xy. So you can do them separately when you've got a difference. A constant multiple. If you have a constant times a function, that's equivalent to saying that constant times the limit of the function. And we know that the limit of f of xy is just L from the assumption up here. Product rule, you have two functions multiplied. Then the limit of that product is the same thing as the limit of the f of xy times the limit of the g of xy. So you would find the limit of f of xy, which is L, times the limit of the g of xy, which is M. The quotient. If you have the quotient of two functions and you know each of the limits exist up here, then this quotient will have a limit that's the limit of the numerator divided by the limit of the denominator. So it'll be the L over the M. And that's only true, though, if that denominator does not have a limit of 0. The power rule. This says a limit of a function to a power is equivalent to taking the limit of the function and then raising that to the power. So there's where you get the L to the N. And the last one here says that if you have fractions m over n for the power, that if m and n have no common factors, in other words, the fraction is reduced, so don't use 4/6, use 2/3, you've got to have a reduced fraction, then the limit of that function to a power will be just that limit of the function to that power, assuming that the L is positive if the N is even. The reason you have to consider that is that this denominator is a root. So you're taking the nth root of that function f of xy, which won't exist if N is even and L's negative. So you just have to guarantee that the L will be positive if the N is an even number in the denominator. So that means you're taking a root, an even root of a positive number. So they're just saying that you can go ahead and just find the limit of this function and then raise it to that power m over n. But that's only true if the n is even, if the L had to be positive. Okay, so let's apply this. You're not going to go through this every time, but we'll do it once. This limit, first we have two things added together. Okay, all we know right now is that the limit of x as xy approaches AB is A. And we know that the limit of y as xy approaches AB is actually B. And we know a limit of a constant is a constant. So those are the basic limits that we have, and we have all of our limit rules. This says that the limit of a sum, we have two things added together here, is the same thing by our sum rule as the limit of 3x squared y plus the limit of the square root of xy. And that's as xy approaches 2/8. Okay, now we've got a product and we've got a constant. So I'm going to use the constant rule that says that this is the same thing as 3 times the limit of x squared y, but because that's a product, I can also break it up to be the limit of x squared times the limit of y. Both these limits will have xy approaching 2/8. And now here I've got an xy to the 1/2. And when the 2 is even, as long as the x and y are positive, I can say that's the same thing as just the limit of the xy to the 1/2. Now, xy isn't always positive, but since I'm approaching the point 2/8, I can assume I'm close to 2/8 so that the x and the y are both going to be positive. So breaking this down a little more, likewise, this limit of x squared is the same thing as the limit of the x squared. This will be the limit of x times the limit of y, using the product rule. Okay, now we've got it broken down to be just constants and limits of x and limits of y, which we know that the limit of x is xy is approaching AB is just the x coordinate, which is A. So this is just going to be 3 times 2 squared. The limit of the y as xy approaches 2/8 is whatever that y value is, which will just be 8. Likewise here is just going to be 2 times 8 So we've got 3 times 4 times 8 plus 16 to the 1/2. So that's 96 plus 4 gives you 100. Now, what this is also telling us is that if this function is continuous, remember continuous functions, the limit was just the function's value. And all we did here was we plugged in 2,8. If you just go back to the original problem and plug in 2,8 for the x and the y, you will get the same exact answer as that limit. So the limit is the function's value at 2,8. And that's true when you have a continuous function.